Hello everyone, I hope you're doing well. In this video, we'll be seeing some of the important formulas and relations in quantum mechanics. If you are beginner to quantum mechanics and even if you are familiar to quantum mechanics, you must know some of the formulas and relations which are frequently used later on. So let's quickly get started with these formulas and relations and note these down. They will help you later in quantum mechanics a lot. Let's see what is the formula for the expectation value, which is also known as ensemble average. So if both of these words are used anywhere, you should know that they both are same. Okay, and they are defined for some observable or operator. Okay, observable means any physical quantity that could be calculated, and it includes position. Position is observable, momentum is a observable, energy is a observable, angular momentum, and so on. And similarly, time is a observable. Similarly, we have an operator for each observable. Okay, for example, if it's position, then its corresponding operator is x bar. If it's momentum, it has some corresponding operator, and if it's energy, it has some corresponding Hamiltonian operator, and so on. Okay, so we have observable and we have a corresponding operator for each observable. Sometimes what happens is that in a question that is given to you to solve and to find out the expectation value, they give you the observable value. For example, they tell you that momentum is actually equals to h cut k. This is not given in terms of operator. Okay, that's not an operator, that is observable. But if they tell you that it is equals to this thing or something like that, or else whatever formula they're using, so that's a kind of operator. There's a difference between observable and operator. In case of operator, you have to be careful about the position of operator, but in case of observable, there is nothing to care about its position, where it's lying, where it's being multiplied, and so on. We know that operators, the order matter in terms of operator. You'll see that why I'm stressing this thing again and again, because most of the students just overlook this fact that observable can be placed everywhere, but operator has to be placed at a particular position only. So let's see the formula. And this is the expectation value for the observable. So what we do is we write the integration over whole space, then we'll have psi star, then we'll have q, and then we'll have psi. Okay, that is the standard positioning of all the things, and you should follow this position, like psi star first, then q, and then psi, and dv. Okay, since it's observable, you can write q here, here, or whatever location you prefer, but I stress this location because when you are given with operators, what you have to do is that psi star appears first, then q operator applies on psi only. Everything that is on the right hand side will be affected by the operator. Okay, so when it's operator that is given to you, for example, when it's, let's say, it sometimes happens that you have Hamiltonian operator and you want to find out the expectation value for energy. So you will use the corresponding operator. You are using corresponding operator, so psi star will remain as it is. Operator will be applied on psi only. You'll solve it and you'll find out the product and then integrate and find out the expectation value. That's how it will proceed. So the location of operator matters. Okay, here it matters. I wrote it in this order for the observable as well, just for you people to learn and memorize this order. Okay, and in case of observable, you can write q wherever you like. Okay, and sometimes what happens is that they frequently mention this formula, that psi star and psi, this product of a simple wave function and conjugate of it is called as the square modulus of psi. So you can write it like that, and this is the probability density as well. Okay, we call it as probability density in quantum mechanics, so we replace it with p symbol dv. That's also a formula when q is the observable, not an operator, when q is the observable. So these are the forms that this formula can get and can appear in front of you, and you should know that they're all same and they are true when Q is observable. Okay, I hope you can get the difference between observable and operator. Okay, operator changes the wave function on which it applies. It doesn't apply on psi star. So if you write operator over here, it just conveys the message that Q operator is applied on psi star and psi as well. That's not true, that's wrong. So you should know the order. So this is the preferred formula that I would tell you people to remember. Okay, and you should know the fact that Q could be placed anywhere and you can write them interchangeably, but in case of operator you can't write it in this form. Okay, that's the final formula for when operator is given to you. And let me tell you one additional thing that is not highlighted by most of the tutors over there. So I can convert this formula into this formula. Okay, really easily we can do that. So let me tell you that how I can do that. Okay, so here Q is the observable, and you should know what is the relation of observable and its operator. Okay, when operator, this is eigenvalue equation that I'm going to mention here. When operator applies on psi, it gives the observable times the psi. Okay, this is the observable, which we also call it as eigenvalue for the operator Q bar. It is like when Hamiltonian applies on psi, it gives E times psi, where E is the energy, which is the observable of H prime. This is just a term that we have, just a name that we have given to each of these things. And you should know that what does observable mean. Observable is actually the eigenvalue, the exact value that we have for this quantity. Let's say if it's energy, so let's say is energy is equals to h squared k squared by 2m, so it will give you like that and so on. So if I have this eigenvalue equation, then from B what we can do is that psi star remains like that. Instead of Q bar psi, we can write its equivalent result, which is Q times psi dV. Okay, and now here Q is the eigenvalue or the observable, so we can replace Q anywhere. We can take it anywhere. So that is kind of simplification that we do normally in some calculations. You should know just that. I mentioned it so that you may not have any confusion between what is observable and what is its operator and what they give. So both of these results, both of these formulas will give you the same thing. If the observable which you are considering here is energy, then this will give you the ensemble average for energy. And if the operator that you are considering here is Hamiltonian, it will give you the ensemble average for energy as well. Both of them will give you the same result if the same psi has been used. Okay, so that's same, just a different thing that you are using. Whether you are using eigenvalue, whether you are using operator, that matters. Okay, this is the formula for the expectation value when we have psi as normalized wave function. And if the wave function is not normalized, then if wave function is not normalized, then we have an extra term in the denominator. So it will become like that. I'm using the operator term next on dv, and it will be divided by psi star psi dv every time. Okay, so let me write it again. It's like that. Psi star Q operator applies on psi dv, and in denominator we doesn't have any operator, it's just the self product. Okay, that's the formula when wave function is not normalized. If wave functions are normalized, this term in the denominator becomes equals to 1. That's what the normalization condition is. So we are left with this quantity. Normally all wave functions that we deal with are normalized, so that is why we mostly have this formula. But you should assure that the wave function that you are considering is normalized. So you have to test it first and then use the formula accordingly. And this is the integral representation of this expectation value, we can also express this formula in cat-bra notation. So let's write the direct notation for expectation value. Okay, so direct notation tells us that, let's say we have the Q operator. We are writing it in general. That is why I'm not using any particular um, operator, let's say Hamiltonian or momentum, etc. So that's the general representation. We have the bra first, and we can see that we have psi star. It will go in the bra section, and we'll write psi only. Star will not be mentioned because it's in bra, and that's understood that it will come out as complex conjugate of psi. So next we have the operator or observable. So here we are considering a operator, so we'll have operator, then another line, and then we'll have the last wave function, which is in cat section since it doesn't have any star on it, and that's it. But if the psi is not normalized, so we will have this product in the denominator as well. So we'll have psi star first in bra section, here line, then cat. There is no observable or any operator involved, so that is it. That is the direct notation for the expectation value. Okay, and if it's observable, the same thing applies. Okay, just you have to remove the operator. Okay, that is it for the expectation value. Now let's see the next formula. Let's see the formula for calculating the probability, and we'll have two different kinds of formulas, and their description would be different as well. You'll see the difference between them. So whatever the case is in your problem, you'll use the formula accordingly. So first of all, let's see the most conventional formula that we see is that, for example, we want to calculate probability of finding a particle in a space region x1 to x2, let's say. Okay, we have some lower limit and upper limit as well, because we are calculating probability, and we'll have some defined limits in which we want to calculate the probability. And let's say the probability is represented by capital P, and it's a function of x and sometimes t. It depends what case you have. So that is equals to this integral. Okay, and we know that what this thing is equals to, this is the square modulus of wave function. So we can open it up into psi star psi and dx. Since it's 1D case, that is why I took dx. If it's 2D, use dx dy and two integrals, and if it's 3D, use three of them and three integrals, and three different limits will be applied. Okay, so it depends what kind of case you have, but in the beginning of quantum mechanics, we always have the 1D cases. Okay, so that is the formula for calculating the probability of finding a particle in between x1 and x2. All right, so that is the formula. And just like in case of expectation value, we saw that the wave function we assumed at first place was the normalized wave function. So the general formula is that we don't know whether the wave function is normalized or not, so we will have this integral in the denominator. Okay, self product in between the limits minus infinity to infinity. Okay, and in numerator we'll have that specific integral that involves the limits that are given in the question. Okay, so we'll have this integral in the denominator always when we don't know whether the wave function under study is normalized or not. If the wave function is normalized, then this whole integral is equals to 1, and we are left with this thing. But in general, you will remember this formula for probability, because and this term, this is actually the normalization integral, and it always appears in all these formulas of finding out the expectation value. Okay, you will have this integral in the denominator for calculating the expectation value, for calculating probability. Okay, in both of these things, in both of these calculations, you will have this integral in the denominator. Okay, and the reason being that the wave function should be normalized. And so I'll say this is a most general formula because it will be suitable for normalized as well as non-normalized wave functions. Okay, so you can remember this formula, and if it is mentioned in the statement of the question that the wave function is normalized, then you can use this only thing. Okay, so it's worth mentioning. You should know the difference between normalized wave functions and non-normalized wave functions. Okay, so this is the normalization condition, that the limit from minus infinity to infinity in the self product is equals to 1. That is the normalization conditions. All those wave functions that satisfies it, the denominator becomes equals to 1. Okay, and that's the exception, and that is normally satisfied by most of the wave functions that we have about the systems that we study in quantum mechanics. So that is it. Now let's see the next formula for finding out the probability, and this is the integral formula, and we cannot express this specific formula in Cat-Bra notation. The reason being that you can see the integral in numerator has limits other than minus infinity to plus infinity, while in Cat-Bra notation it's always understood that the limits that we are considering are minus infinity to plus infinity, the maximum that is possible for the system. So it is not practically, for now, as a beginner, possible to specify these limits in Cat-Bra notation. Okay, we'll see the Cat-Bra notation in a different context for finding out the probability, and the description will be different in that case. Okay, so let's see the another formula for calculating the probabilities. Okay, I hope you are clear. This is the general formula for probability, and we saw this. Okay, we can use Q formula. This is the formula for expectation value. Okay, and we can see these are the general ones. All right, now let's see the another formula for finding out the probability. That a system is in state, is in some state psi n. We have to find out the probability that a system is in the state psi n. Okay, we are talking about now states, the possible states the system could have. It now normally it happens that a system could be at psi 1 state, psi 2 state, psi 3 state, psi 4 state. Okay, and psi is actually equals to the linear combination of all the possible states that the system could possibly have. Okay, so you can understand it like you know that electron can be at spin up state or spin down state. So its general wave function is represented as linear combination of spin up state plus spin down state. We say that the electron could be at spin up state as well as in spin down state. These are the two possible states the electron can have in terms of spin, and normally in all of the system that we consider, there are multiple states the system could be at. Okay, for example, it could be at first excited state, second excited state, third excited state, or fourth excited state. So how we can express that kind of system in general? We write them as the linear combination of all those states. Okay, and now what if we want to calculate what is the probability that the system is at the ground state? Okay, by psi n state means that we are taking some specific state and we want to find out the probability that the system is at this particular state out of all the possible state it could be at. Okay, I hope you are understanding. The interpretation here is different than this one. It's totally different. So the requirement in the problem statement would be in this way. Okay, that was the probability that the system is at ground state, and what is the probability that the system is at first excited state, what is the probability that the system is at second excited state. So how we can calculate that probability that a system is in state psi n, where psi is the general wave function for the system. where psi is the general wave function of the system that is equals to the superposition of all the possible states the system could be at. Okay, so let's see the formula. Probability in some n state, I'm taking n as some general term, so that's really simple. We'll use the Cat-Brown notation here. We'll have psi n first, in which the probability needs to be calculated, then the scalar product with psi. Okay, and in general we'll divide it by this integral again for the sake of normalization of the wave functions. Okay, so that is the general formula. You can see that's really simple. You can write them in integral form as well, and you can even solve it using the Cat-Brown notation. So that is the formula to calculate the probability of a particle or a system to be at psi n state when psi is the general state. So we can write it in integral form as well, since it is written in Cat-Brown notation. So you can write it from minus infinity to plus infinity powers, and that is the formula. Okay, that is the formula to calculate the probability of a particle to be at psi n state, and that is the formula. All right, so we have seen two different formulas for calculating the probabilities, and the first formula is, we saw that probability equals, we have minus x1 to x2 psi star psi dx divided by minus infinity to plus infinity psi star psi dx. That is one of the formula, and you can write the denominator in Cat-Brown notation. Oh, sorry, you can write the denominator in Dirac notation, whereas numerator couldn't be written in that way. So that is the first formula for calculating the probability of finding out the particle in space region x1 to x2, while the another formula of finding out the probability that the system is in psi n state is given by this integral. Okay, and this compulsory thing factor in the denominator always. All right, these are the two formulas, and we'll see the application of these formulas that will clarify you when to use them and when not. Okay, you should know that when the given formula is not applicable. All right, that is half of the understanding that you should have about the system. It reminds me of one of the quote by Edison, who actually invented a bulb. He said that I tried to make a bulb like 1,000 times and I failed 1,000 times, and it is not a waste of time or something like that. I'll say that I now know that in what 1,000 ways, in that particular 1,000 ways, a bulb couldn't be made. Okay, so that adds to your understanding as well, that what doesn't work and when it will not work. You should recognize that. You should learn that when these formulas are not applicable and when they are applicable. Let's see the formula to calculate uncertainty associated with any observable, let's say q, or we can say operator as well. So let's see the formula. I'm using delta q as a symbol to represent the uncertainty associated with q variable, okay, or observable you can say, and we can also represent it to be equals to the sigma sign. It depends upon you which notation you are preferring. You can put q in the subscript to show whether it's uncertainty in position, momentum, energy, or whatever. Okay, I'm using q as general representation of any observable, so that is equals to under root of ensemble average of q square, okay, minus ensemble average of q and a whole square of it. Okay, that's the formula of calculating the uncertainty associated with variable q. Okay, and if it's position, you'll write x x x everywhere, and we'll see the example later on. This what this equals to, how we can calculate these two quantities, because if we know these two quantities, we'll plug these quantities into this expression and we'll calculate the uncertainty. So we can see that q square is ensemble average, and we know the formula to calculate ensemble average. We saw it right now. Okay, it's minus infinity to infinity. We'll have psi star first, then the quantity whose ensemble average we want to calculate, it's q square. So you'll write q square here, psi, And dx, it depends whether the system is 1D, 2D, or 3D. Normally in the beginning it's 1D, so I'm using dx. You can use dv for general representation. It's totally sensitive to the case you have. Psi star psi dx, because that's always there until and unless the wave function is normalized. Okay, I'm writing the general cases now. And next we have this thing, because that is how we that is what we need. And after we calculate it, we can take the square of it. So it's minus infinity to infinity psi star q psi dx divided by this. All right, and we can also represent it in Cat-Brown notation simply like that. Okay, and here we have this thing. That's super easy, and we are supposed to calculate these two quantities from the formula of expectation value. Okay, we'll plug these values right back into this expression. We'll write this quantity right away. We'll write this quantity here. We'll take the square of it, subtract under root, and we got the uncertainty associated with the observable. Okay, let's say the observable we are considering is position. We want to calculate the uncertainty associated with the position in some system whose wave function is psi. So x is the observable or the symbol that we use for position. So we'll have delta x. Uncertainty in position would be equals to sample average of square of it, okay, minus sample average and then whole square. And we know the formulas that we can write really easily here. It's that psi x square psi in Cat-Brown notation, because it is a concise way to write it. Just quickly, you can see how easy it is. So that is how you are supposed to calculate uncertainty associated with any variable. Okay, and if it's operator, you'll put operator over there. That's simple. Wherever there is observable, you can put hat over there to show that they are operator, and they will give you the same result. They will give you the same uncertainty associated with the observable whose operator is this quantity. If it's Hamiltonian operator, it will give you the uncertainty in energy. They both, observable and operator, both of them give you the same information. Okay, so the treatment is slightly different. When it's operator, you have to be careful. And yeah, that's it. Now there is a relationship between uncertainty and this and standard deviation. Actually, they are equal to each other. Okay, both of them have same formula. So if they ask you to calculate the standard deviation in position or in any observable, you'll use the same formula. Uncertainty and standard deviation are the same quantities, and you should know it. Okay, and there is another term that we see, it's dispersion. Okay, and they are really, closely related. So dispersion is actually equal to the square of uncertainty or square of standard deviation. Okay, so uncertainty, I'm representing uncertainty by delta q, so its square will be the dispersion. So sometimes they ask you to calculate it. So that's a general and really easy formula, so you should know it. Under root, that is uncertainty, and we'll take the square of it. Under root and square cancels out, and dispersion is actually equals to q square ensemble average minus q ensemble average whole square. We'll do a ton of problems related to these. You will see how to apply these formulas, so don't you worry. You just should know the formulas. Okay, that is dispersion, that is uncertainty. Okay, in general, for position, you can write it for energy, for any observable you are interested in. Okay, so these are the formulas. You must be wondering that why I'm not talking about uncertainty relation, because that's a really important relation in quantum mechanics. And the reason being, we know that in you must have seen in FSC studies and other high school studies that sometimes they tell you that this is equals to h cut by 2, and sometimes they write it like that. You must be confused that why is it so. why there is, what it actually equals to, and how we can know that. So I'll be considering and addressing all of these questions all in one video. So there will be a dedicated video to uncertainty principle, and we'll see all of the things and facts about uncertainty principle in detail. Okay, and that would be a bomb video. So yeah, stay tuned for that video. And now I'm gonna mention some of the formulas like operators and Schrodinger's equation in a next part, which I already uploaded in a separate video, but I thought that they were important and you should know those formulas. So if you have already attended the video where I've talked about the operators in quantum mechanics, so you can skip the next part that is coming up. But if you haven't watched that video, you can watch the rest of the video to note down all of the important parameters or operators and equations in quantum mechanics. I want to mention these operators in quantum mechanics that are really important. I have a dedicated video to these operators if you want the further details and explanations. So this is the position operator, and position operator is simply represented by putting hat over the symbol you are using for representing position. It's a simplest operator that we have in here. So it's x, y, and z operator in 1Ds. And if you are considering the 3D case, so as we already know in vector algebra, that r is equals to xi hat plus yj hat plus zk hat. So if you are considering a 3D case, then it's simply r hat equals x hat I hat plus y hat j hat plus z hat k hat. Here a I hat, j hat, and k hat are the unit vectors, while x hat and y hat and z hat are actually the operators. And that's the simple transformation from 1D to 3D case. It's always the vector sum of the 1Ds. Okay, and we can see the momentum operator. These are the basic operators, and it's simplest. And we can see in momentum operator, it's not only px, it's actually equals to minus iota h squared partial by partial x. Okay, unlike position operator, this is equals to something that operates on psi function, wave functions, and changes the wave function in a particular way, while the opposition operator doesn't changes the wave function on which it is applying. So momentum operator is equals to, in x direction we use x, in y we use y here, in z we use z here. But if we are considering the 3D case, what we do is to sum up all of these, okay, with I hat, j hat, and k hat. And if we take iota h get common, then the things that are inside of it are partial by partial x plus partial by partial y plus partial by partial z, which is actually the del operator. So that's the operator, p operator in 3D. And we can see that in x it's a minus iota h get, only this part is changed. In x it's partial by partial x, in y it's partial by partial y, partial by partial z. In 3D it's del. Okay, you can remember it in that way. Hamiltonian operator, this is the Hamiltonian operator in 1D, and it's equals to minus h squared by 2m partial square by partial x squared plus v. Operator v is the potential energy, and it's operator over rate because it's actually expressed in terms of operators. And in 3D we can see the same thing, minus h squared by 2m remains the same. Instead of this operator you'll write delta square plus v. That is the Hamiltonian operator in 3D, and that is the Hamiltonian operator in 1D. Wherever it's partial by partial x or partial square by partial x square, replace it with delta sign and you are getting it in 3D, where delta is actually equals to this thing. Okay, so next we have Schrodinger's equation. And apart from the fact that this is the Hamiltonian operator in terms of space variables, this is the Hamiltonian operator in time space. Okay, Hamiltonian equals iota h squared partial by partial t. That is the Hamiltonian in time space. So that's also a formula for Hamiltonian, and it's used in time dependent state. So time dependent form of Schrodinger's equation is obtained by equating this Hamiltonian, position dependent Hamiltonian, with time dependent Hamiltonian. So that is how we can see here that this is iota h squared partial by partial t applied on psi. I have applied psi on both of these sides. You can see iota h squared partial by partial t. This is Hamiltonian, time dependent Hamiltonian. Okay, and this is the position dependent Hamiltonian. Both of them are applied on psi on both sides. So we have equated both of these Hamiltonian actually. Okay, You can see this is Hamiltonian, the same one. We have equated the space dependent Hamiltonian with the time dependent Hamiltonian and psi on the right hand side to complete the equation, and that forms the time dependent form of Schrodinger's equation. That's so easy to remember if you know what is space dependent Hamiltonian and if you know what is the time dependent Hamiltonian. Equate them together and apply psi on the right hand side, you have got the time dependent form of Schrodinger's equation. Okay, and I will link down the video where I have derived the time dependent form, and out of which we have derived the time independent form as well with detailed derivation. You can check them out. Here I'm mentioning the equations and relations only that you should know. Here we have time independent form. In time independent form, we use the eigenvalue equation. Here H applies on psi. It gives E into psi, where E is the eigenvalue of operator, and H is only space dependent. There is none of the time dependence factor in them. So you will simply write this thing, psi of x, E times psi of x. You can see the difference between time dependent form and time independent form. Time dependent form has the time in each of these in wave functions, in potential, and here on the right hand side as well, while time independent form has x dependent, space dependent potential, space dependent wave function, and E as constant on the right hand side, and time variable is eradicated completely. Okay, that is the time independent form of Schrodinger's equation, this, and you can write it like that, like that. Okay, that's so simple. And we have got this wave function, time dependent wave function, coupled with the time independent form, and you can see its reference from the derivation. And yeah, that's it. You must be wondering that why I haven't mentioned the uncertainty relation here, and I'll tell you, I'll make a dedicated video on uncertainty relation, and to tell that what it is actually and what it equals to. Actually, sometimes students just get confused that sometimes we have delta E times delta T is less than or equal to H cut, and sometimes they tell us to write H cut by 2, and so on. We are just confused that is it equals to H cut or it is equal to H cut by 2, exactly what it equals to, and exactly what the uncertainty relation is. So I'll answer all of these questions and I'll clear all of your doubts in a dedicated video on uncertainty relation, because it's really important topic in quantum mechanics. That's the basis and the starting point of quantum mechanics, where we see the uncertainties related to all of the parameters in quantum mechanics. So we'll be dealing it separately because it's something worth discussing as a whole. And I link all of the important videos that I recommend you people to watch. It depends upon you, and you can see those videos in description box. Okay, I'll link them in the card so you can check them out, and check out the playlist quantum mechanics, and let me know if you want any other special video on any of these terms that I have mentioned here, if you want me to discuss them in detail. So I'll do that, and stay tuned with the problem solution that I'll be doing. I'll explain all of these things in detail. So I hope you got it. Like, share, and subscribe. Goodbye.